Hi, so in this video, we're going to talk about how to implement a stack that can store data based on the linkless space stack that we implemented earlier. So we've implemented the stack class. However, it doesn't seem to be very useful because all it can store are just nodes and it cannot be used by any client code to store any data that the user might want, such as an integer or strings or other user-defined data types, right? But the good thing is the stack class actually defines the operations that a stack can support, right? The push and the pop and is empty and that sort of operations. And that, as a matter of fact, for a linkless base class like stack, it's actually could be the majority of the work. So those have been done. So all we have to do now is to add the capability to allow client code to store data. Then the question is, how do we do this without duplicating the entire stack class itself? The answer is inheritance, the topic that we've been studying. So we can just create a new class that inherits from stack and then add the ability to store the data. Now, the question is, where do we store the data? So when we think about it, we can potentially store more and more data, right? So that means the data is going to grow. So the thing that can be grown in a stack class is the number of nodes. So very naturally, then we will probably want to store each piece of data into its own node so that we can create more nodes to store more data. So the first thing we're going to do is then we are going to create a data node that inherits from the node class, and we're going to store data in the data node. And that would be this code, data node, inherit from node. And the initializer is going to take the piece of data that is going to be stored in the data node. And now remember that we have to explicitly call the base classes then the init method, right, which would initialize the next pointer or attribute. And then in the data node itself, we're going to create a data attribute that would store the data. And while we are at it, we might as well define the string method. Now, it depends on our needs. We could call the super dot string, but in this case, the super string, the nodes string, it's going to print out the ID of the node itself, which it's useful for node because there's really no other identifier for node. But for data node, we could just convert the data into a string and use that as the string representation for data node. And the data is a recognizable piece of information for the client code. So that could be a good choice there. Now, the next thing we're going to do is we are going to implement what's called DataStack. So just like the data node, which inherits from the node and add the capability to store data in the node, DataStack is going to inherit from stack, and it's going to provide the capability for the client to manipulate data, to either push data or pop data. So we're going to start with that. DataStack inherits from stack. And the first question is always, what do we need in the initializer? Do we need to do anything differently for DataStack than for stack? Well, the answer is not really, right? Because when we start with the empty DataStack, it's an empty stack as well. So there's no data. So there's really nothing special for the initializer of the DataStack. So we can skip that. And the next thing is Okay, what about the push method? Now, so the push method, we are not going to push nodes anymore, right? Because this is for end clients and DataStack deals with data. So we're going to take a piece of data from the client code, and again, an integer, a string, or any user-defined type, etc. So that will be our parameter. And now we are going to wrap this piece of data inside a data node. So we're going to construct a data node and pass the data to it. And then finally, we are going to put this data node in the stack itself. So we simply use stack.push or super.push and push the node in there. Now, so and this push method is fairly simple, right? And the reason that it can be so simple is that the stack.push or super.push, it's already kind of taking care of where to insert the node. So there's nothing for DataStack's push to do really, other than to construct a data node and use stack.push to push that. So this is another very, very good example of encapsulation or kind of a separation of responsibilities that stack deals with data structure. The stack deals with the structure of the linked list, whereas DataStack is responsible for data. So one final thing I want to point out is that even though stack.push expect its parameter to be a node, and here we're pushing a data node, but we know that by inheritance, data node is a node. So this is going to work fine. Now next we should write DataStack.pop that returns the data at the top of the stack. And after seeing the example of how to write the DataStack.push, I'm hoping that you can actually try to give this a shot. And here is the code, which is very short. Remember, the client is expecting data. So the first thing we do is we call the stack.pop or super.pop to get the node at the top of the stack. And then obviously we don't want to return the node, but we extract the data from the node and return that. And this is another example of encapsulation, that here we are not concerned of how to get the top of the stack, but we just use stack pop method to get that node, and then we just deal with the data in the DataStack.pop method. And the next question is, what do we do with DataStack.isEmpty? Is there anything different that we have to do? And the answer is no, there isn't, because when you think about it, whether stack is empty or not really has nothing to do with the type of data that is in the stack, right? It's a structural feature of the class. So all that we have, we can just leave that to stack itself. So one more question. And so what do we do with the DataStack.string method? Do we have to do anything different? Well, I guess we would have to include the data in each of the node, right? And the answer is actually no. Because we've already done that in the data nodes.string method, and the stack.string method will actually call the data nodes.string method and includes the data in its string representation. And when you think about this a little more deeply, you would this is actually quite a really nice thing that it happened that way, particularly because the stack.string method was implemented before the data node.string method. And let's take a look at how that actually happens. So here I allocated a data stack, and I'm going to print it out here. And when I print it out, it's going to call the DataStack.string method. Now, we're not going to define a string method for DataStack, so it's going to call the base class of DataStack, which is the stacks string method. Now, and in this method, it's going to loop through all the nodes in the linked list, and for each of those nodes, it's going to call its string method to try to get a string representation of that node. Now, this node, remember, this is a data stack. Therefore, each of these nodes are actually data nodes. So here it's going to call data nodes dot string method, and data nodes string method only includes or already includes the data in that node. So when this string, the whole string representation, when it's completely built, it's just going to include all the data that are in each of the data nodes of the data stack. All right, enough talk. Let's see this code in action. So I've already typed out the code here, data node, data stack, and I allocated data stack here. And then I'm going to push data, actually in this case, integers, onto the stack. So as the client of a data stack, I don't want to deal with nodes and things like that. And thankfully, DataStack hides all those details from me. So I push the numbers, I'll print out what's in the stack. I'm going to pop something, check it again, and finally check if it's empty. So let's see if this works correctly. So, all right, so DataStack at the beginning, it's empty because there's nothing in it. And then after we do, actually not 2 pushes, 3, we're going to have the numbers 3, 2, and 1. And 3 is at the top of the stack. It's the last one that's pushed. So when we pop it, we see that 3 is popped. And after we pop, what's left in the stack is 2 and 1. And the stack is not empty. All right, so it's a summary for the data stack, and you can see the code for the data stack. It's very short, and the reason that it can be so short is that it's entirely focused on its very distinct responsibility, which is to deal with data, right? And the other reason that it can be so short is the hard work of dealing with the structure of a linked list-based stack that has been taken care of by the stack class itself. So these two classes, they perform very different, distinct functionalities, and their functionalities are very well encapsulated in the respective classes. So I hope you understand and appreciate the beauty of encapsulation in this example.